For the second part of 4.2, we're going to get into curve sketching, where we use our points, our intercepts, the known fact for the domain, the first and second derivatives of where it's increasing, decreasing, our local max, min, our inflection points, and graph the function. So yes, we could just put these in a calculator, graphing calculator. However, on the test, you will have to be able to do and show the work of how the calculator got that graph, besides just plotting points. So the first step is to analyze the original function, domain, and the intercepts. Second step is to analyze the first derivative. Where is it increasing? Where is it decreasing? Is there a local max and min? Third step is to analyze the second derivative. What are the partition numbers, inflection points, concaving upward and downward, and then use all of those points and sketch the graph. So first step, here's our function, is to come up with a domain, x-intercepts is when it's equal to 0. So we get x equals 0, x equals 3. Y-intercept is when you put 0 in for x, you get 0. Okay, second step, I'm going to shrink that. Second step is first derivative. Critical values. Increasing and decreasing, so negative value in there, I'm going to get negative times a negative. Put a 1 in there, I get a negative. Put a 3 in there, I get a positive. So we have increasing, negative infinity to 0, decreasing between 0 and 2, increasing from 2 to infinity. We have a local max at 0 and a local min at 2. Oops. Let me shrink that. Okay, next step. Second derivative. Critical values. Less than 1 is negative, greater than 1 is positive, so it's concave down from negative infinity to 1 and concave up from 1 to infinity, and 1 is an inflection point. So let's go ahead and come up with some of these points. So we know 0, 0. 2 in our original function. 2 in our original function is -4. And let's do that inflection point. Put 1 in our original function, and we get -2. So then the last step is just to graph this. Zero, 0, 2, -4, 1, -2. We know it's increasing from -infinity to 0, and it's concave down. From 0 to 1, it's concave down and decreasing, concave up, and still decreasing from 1 to 2, and then from 2 to infinity, it's concave up and increasing. And you try match problem. Okay, for the matched problem number 5, I already put the answers up here, so I want you to take a few minutes, look at what I got with the domain. It's a polynomial, it's all real numbers, x and y intercepts, the increasing, decreasing, there is a local min, the concave up and concave down, and a graph. And the graphing, it really is just relative. Okay, when we look at an application of this second derivative, we introduce new vocabulary, which is the point of diminishing returns. And I wrote the definition up here. The point of diminishing returns is that amount at which the rate of change, first derivative, goes from increasing to decreasing. We can also say it's the amount at which the rate of change has a maximum value. So if we want to find that number, that's our inflection point. So we need to actually find the second derivative and find that inflection point. And then that max value is going to be the inflection point's y value. So in the first derivative. So let's look at this. Let me try to make more sense with the actual example. So we want to find the rate of change, the sales increasing and when it's decreasing, and the point of diminishing returns, and that maximum rate of change, okay, maximum rate of change in sales. So the first thing we're going to do is find the first derivative. Find our critical values. Which is 0 and 9, which happens to also be our range. Going to find the second derivative. So now I need that inflection point. So we get 0 and 6. So when is it increasing and decreasing? Looking at, we can't be less than 0 because our domain is from 0 to 9. So from between 0 and 6 is going to be positive, and from 6, and we have to put a 9 here because that's our domain, and from 6 to 9 is going to be negative. So it is increasing the rate of change is increasing from 0 to 6 and decreasing 6 to 9. Our point of diminishing returns is x equals 6, because it's the inflection point. It's where does it change from increasing to decreasing. And that maximum rate of change is then finding it at the first derivative. So putting 6 into first derivative, we will get 108. If you want to graph them on the same coordinate, like it suggests, I'm going to shrink this so I have some room. Two, three, 4, 5, 6, 7, 8, 9. I'm going to count by 200s over here. 2, 4, 6, 8. We know that at 6, this would be your first derivative. And second, or the original function would look something like that. Okay, so you try match problem number 7. Okay, so I put the match problem number 7 on here for you. Hopefully you were able to find your critical values of 0, 8, and 12 between the first and second derivative. Your point of diminishing return is 8, and the max rate is 256. And the graph, if you needed to graph them, would look like so.